Good evening or morning or whatever we've got here. Today I'd like you to take a look at the program for this, which is a Mathematica sheet. And it's got just a few commands on here, and no verbiage. So I'd like you to add text after the video, or during the video you can stop it and put some text in. But this is the first video about, or first work on, how to handle functions from one Euclidean space, higher dimension than one, like in this case the plane, with the domain into the real numbers. So the range into the reals. So these will be real valued functions, meaning that these map into the reals. Something like a temperature function. The temperature function in the plane might look like this. The temperature at any given point is given by this equation. And in what I have, everything will lie in a square between -10 and 10. So we'll have the usual x and y axes. And all our temperatures will be from in this region right here. And the temperature at any given point, like 1, 2, is given by this formula. So the temperature at 1, 2 is 1/5 plus 8/5, 9/5 is the temperature at 1, 2. So I'll put that in red here, meaning that that's the temp at that point. So we want ways to look at this function and analyze it both geometrically and we want to analyze it what's called analytically using calculus. And we'll do a little bit of both right away. So let's start with the analytic business. This thing has two slopes. It has a slope in the x direction, which would be given by the derivative of this function with respect to x, the temperature function with respect to x. And if you just take the derivative with respect to x, treating y as a constant, you get 2x over 5. So this is a formula that will give you the derivative with respect to x at any given point. And similarly, the temperature at a point xy with respect to y is 4y over 5. So these are easy to compute. This is not the notation we'll use, but I'm using it right now just to indicate it. And these derivatives give you the slope of the graph in the x direction. So I'll call this m sub x and this m sub y. They will be the slope, the rise over run of the graph of this function at any given point. And we'll use these computations later on. So we can begin to investigate analytically by finding these partial derivatives. There is a total derivative called temp prime of x and y. And temp prime is just the ordered pair of these. In general, derivatives are always matrices. So in this case, it's 2x over 5. And 4y over 5. For those of you who've taken a little physics, the derivative of this kind of function is called a gradient. So this is called the gradient function, but it is the derivative of this function. And the two components of it give the two slopes, slope in the x direction, slope in the y direction at any given point x and y. So the slopes at the point we computed here, 1, 2, the slope in the x direction is 2/5, the slope in the y direction is 8/5. So if we look at the tangent plane at the point 1, 2, the tangent plane, and this surface for the graph will have a tangent plane. The slope in the x direction will be 2/5, and the slope in the y direction will be 4 times as much, 8/5. And so at 1, 2, and the point on the graph, this will be the tangent plane. And we'll compute that a little later. The graph of this temperature function will be in 3 dimensions. The domain has 2 dimensions. The range has 1 dimension. And so the graph lies in 3 dimensions. But more generally, this is the last time we're going to be able to analyze the graph by looking at it. If the domain was 3 dimensions and you had a temperature function in 3 dimensions, then the graph would lie in 4 dimensions and the graph becomes more complicated. So for a minute now, I'd like to share this sheet that I gave you, if I can find it on here. There we go. So here is the sheet that you should be looking at. If you enter these first couple of lines, then you get the equation, the temperature equation, and at any given point, and the temperature evaluated at 1, 2, which we did and got 9/5. The next line finds the derivative of temperature with respect to x, and then comma, the derivative of temperature with respect to y. So that is a computation of the derivative. The next line is again a computation of derivative, but this time I plug in the point /dot, means substitute in 1 for x and 2 for y. Tell me what you get. And you should get the ordered pair, 2/5, 8/5. And these are the slopes that you're going to use. So using Mathematica to do the analysis occurs on those first 5 lines. And now we'd like to look at a couple of plots of this. So let me look at the contour, region, and density plots first. And I'll go back to the board. So I'm going to erase a little bit of what we got here, erase the slopes. Slopes have to do with the graph. Contour plot is not about the graph. It's about looking at the domain, which in this case is -10 to 10 in both directions. At each point in this 100 square acres, or 100 square miles, whatever it is, every point's got a temperature. And we could look at all the points that have some specific temperature, like 20. Where are all the points that have temperature 20? And if we do that, we get some kind of an ellipse whose equation is x squared over 5 plus 2y squared over 5 equals 20. And this is called the contour of level 20 for this temperature function. And the next lines on your sheet work with this. The very first line after the 6th line is exactly this. We're going to look at the contour where the temperature is exactly 20. And the equal sign in there is not a normal equal sign. This is a double equals. That's telling Mathematica to set this equal to 20 and find those points. If you use a regular equal sign, it won't do anything. Just sort of duh. The next contour plot, which you've probably gotten if you entered that cell, doesn't have an equal 20 on it. It is just a contour plot of the function. And at the very end of that line, I tell it to plot me 5 contours. It will color your contour areas, and you can control those colors. But right now, we're just interested in how to see these contours. So in this case, it will give you 5 contours and the little regions between. If you take your mouse and mouse over those, as you cross a contour, it will tell you what the contour is that you're crossing, 25 or 32, whatever it is. So these contour plots are one of the ways that you look at functions of several variables, real-valued functions of several variables. The next one is interesting. It's a region plot where you can specify looking at a range of temperatures, say between 5 and 50, and look at all of the temperatures between 5 and 50. If you do that, you get a little annulus of temperatures, a ring of temperatures, but it's not a circular ring. And I colored that ring with red. You can plot style works with region plot. It does not work with contour plot. Density plot is very similar to contour plot, but it shows you it doesn't show you the contours, but it shows you the rise and fall of temperatures pictorially in a different way. So the color changes to red as the temperature rises, and blue as the temperature falls. And that's because I used this rainbow method, but there are other methods, color methods of showing this. These are typical ways of looking at pictures and analyzing such a function geometrically: contour plot, region plot, and density plot. But in this one, we can actually look at the graph. And I thought we'd take a little look at that. We can look at the graph and plot it in two ways. First of all, we can use plot 3D and plot this as just a temperature function. So in plot 3D, you're plotting the temperature of xy. And then you specify the range, the domain values as usual. And this will plot it. I think I put in a color in here also. But this plots the temperature, and you get a certain plot of it. We can also use parametric plot. Because the graph is in 3 dimensions, it's parametric plot 3D. And now this is a little different. We're going to plot 3-dimensional objects. So we're going to have an x, a y, and a z. And for my first parametric variable, I'm going to use just plain old x. And for my second parametric variable, I'll use plain old t. So this will be my x, this will be my y, and my z will be s squared over 5 plus 2t squared over 5. And these are the points that I'm going to plot. These are exactly the points on the graph, and that's what parametric plot does for you. This time s will go between -10 and 10, and so will t. This has advantages because you can also set the x, y, z axes with other things. You can also color this a little more robustly than you can with plot 3D. But this is enough to do it. Parametric plot 3D. And in your in lines on this little paper, when you graph these, I think they're both in magenta, they do not look identical. They are the identical graph over the identical domain, but the graphs look different from each other. And so I'd like you to look at these. Now, in class on Wednesday, we'll talk about finding the tangent plane to this graph at the point 1, 2, 9/5 on the graph. So we'll actually find the tangent surface here. We'll find it both parametrically, and we'll find it in terms of the Cartesian coordinates. And then I'd like you to plot that tangent plane together with the surface in both of the graphs that we have. So as an exercise, you might compute the tangent plane and plot it together with this Cartesian surface, find the tangent plane in parametric form, and plot it together with the parametric form. so that you should get a feeling for doing those together and seeing that they fit together. There's one other part of this that I'd like you to take a look at, and that is what happens if you have a domain that is higher dimensional than two-dimensional. So suppose that you have a temperature function in 3 dimensions. And I gave you one here to work with. Now the graph is sort of unavailable to you. Now you're working not with the graph, but you are working, the geometry will be different. And so here, contour plot and region plot are more important in terms of analyzing the behavior of this function. And I gave you a couple ways to look at that at the bottom of the sheet. Contour plot 3D, and I guess contour plot 3D in 2 different versions, but region plot also works in 3D. Okay, so that's enough for today, short and sweet, I hope. On Wednesday, we'll do a little tangent surface. We'll play around with these, and you can check out your homework assignment, because that too will have some problems that you can work on between now and then. Thanks a lot. See you Wednesday.